Welcome to A Day in the Life of a Database Administrator. After watching this video, you will be able to describe a typical day for a database administrator and identify common tasks a database administrator performs. This is Rigel, a database administrator, or DBA. Grabbing a coffee, he starts his day by checking that the databases he is responsible for are all up and running with no errors. Rigel uses pre-configured dashboards to make sure he gets the most crucial information quickly and easily. Today's a good day. There's only one minor alert that Rigel resolves without issue. The next activity of the day is to check that the scheduled overnight tasks ran. Rigel checks that the scheduled backups have completed and double-checks the schedule for tonight. Happy that the dashboards and scheduled backups haven't revealed any problems, Rigel checks his email. He's looking for user requests. Usually these will arrive as support tickets from the self-service portal or the help desk. Today he finds 4 support tickets and an email from a developer in marketing with whom he has worked before, asking for a feature improvement. Rigel triages the support tickets and plans how he will respond to them. Some users are requesting assistance with slow-running queries, so Rigel reviews query plans and helps with some query optimization. The developer in marketing is requesting additional fields for a database that tracks the results of a marketing campaign. So Rigel discusses the changes required to the database schema with her and asks her to submit the request through the self-service portal to track and document the response. After a quick lunch, Rigel attends a planning meeting for a new database. Attendees include developers, data engineers, and data architects. He's working with them on a database design to ensure high read performance for a business intelligence workload. He'll make sure that the appropriate resources are allocated for future user base growth and develop a stress testing scenario to find out the maximum load the database can handle. DBAs like Rigel use analytics to determine appropriate server resources like storage space, RAM, processing power, and log file size. Rigel heads back to his desk to finish up his day. He spent some time configuring an alert to be sent to his mobile phone, and now he'll know immediately if the alert gets triggered. As he works, he keeps an eye on his email, watching for support tickets. A couple arrive, and Rigel deals with them swiftly. Just before packing his bag, Rigel makes some final checks. He reviews the dashboards and checks he has scheduled the overnight tasks correctly. Happy with a good day, Rigel heads home. Tomorrow is another day. In this video, you learned that a typical day for a database administrator includes checking the state of the database and resolving any issues, responding to support tickets, meeting with developers and other stakeholders, and monitoring database activity. Welcome to Database Lifecycle Management. After watching this video, you will be able to identify the stages of the database lifecycle, list common tasks within each stage, and recognize stakeholders involved in decision-making during each stage. The database lifecycle splits into 4 stages: the initial requirements analysis, designing and planning the database deployment, performing the actual implementation, and monitoring and maintaining day-to-day operations. In the requirements analysis stage, DBAs like Rigel work with data engineers to understand the purpose and scope of the database. Rigel and the rest of the design team must establish what data is involved, talk to the users and producers of that data, and develop samples of how users will use the data, such as reports or dashboards. Rigel and the design team work with the stakeholders to determine their requirements. Stakeholders may include developers, data engineers, administrators, or end users of the application supported by the database, technology managers, and other DBAs. A few of the tasks they might perform include analyzing the need for the database, clarifying the goals the database fulfills, and identifying the users of the database. In the design and plan stage, Rigel's job is to develop a plan for implementing the database. To do so, he works with database objects such as instances, databases, tables, and indexes. A database model represents the design of a database. Which instance contains which databases and tables, how the tables relate to each other, how users access the data, and so on. Database architects and DBAs model the databases and their objects with the help of entity relationship diagrams, or ERDs. In self-managed environments, such as on-premise databases, DBAs also need to consider size, capacity, and growth. They determine appropriate server resources like storage space, memory, processing power, and log file size. They also need to plan for how database objects are physically stored. For example, DBAs can choose to store frequently used data on a high-speed disk array or to store indexes separately from the data for better performance. In the implementation stage, DBAs roll out the carefully planned design. Rigel creates database objects like instances, databases, tables, views, and indexes. Another task Rigel performs is configuring database security, granting access for database users, groups, and roles so database objects are accessible only by the specific users and applications authorized to access them. He also automates repeating database tasks such as backups, restores, and deployments to improve efficiency. In populating the database, he might import data from other databases, export data based on a query from a different source, or migrate projects from one environment to another, such as moving a project from the application development environment to the production environment. In the monitor and maintain stage, Rigel looks after the daily operations of the database. He will monitor the system for long-running queries and help end users optimize them to run faster and not overuse system resources. A key part of Rigel's job is to review reports. Most relational database management systems have built-in reports to monitor activity, identify expensive queries, resource weights, and other relevant items. Often, companies build custom reports on top of these, and DBAs help with that. To keep the databases working at top efficiency, Rigel may also apply upgrades and security patches to database software. He needs to stay up to date on issues and advancements in the field so he can recommend and implement emerging database technologies. Rigel might also automate deployments and routine tasks, such as backups, whenever possible to keep processes working efficiently. In every database, operational issues will sometimes arise. Rigel troubleshoots these issues, escalating problems where necessary. DBAs are responsible for keeping data safe. Part of Rigel's job is to regularly perform user audits and ensure that only authorized users are allowed to get into the system and that users can only see things they are supposed to see. Rigel reviews logs and alerts looking for failed logins and data access attempts to identify potential threats and vulnerabilities. He also maintains database user and application permissions, revoking access to users and groups who should no longer have access, and adding new users and roles as required to perform their jobs. In this video, you learned that the database lifecycle stages are requirements analysis, design and plan, implementation, and monitor and maintain. In the requirements analysis stage, DBAs determine the purpose and scope of the database by interviewing data users and producers, examining the data, and creating samples. In the design and plan stage, DBAs work on logical and physical design. In the implementation stage, DBAs deploy the database. And finally, in the monitor and maintain stage, DBAs manage the daily operations of the database. Welcome to Database Objects. After watching this video, you will be able to recall the hierarchy of database objects, describe an instance of a database, define the term schema, and list commonly used database objects. Relational Database Management Systems, or RDBMSs, contain many objects that database engineers and database administrators must organize. Storing tables, constraints, indexes, and other database objects in a hierarchical structure allows DBAs to manage security, maintenance, and accessibility. This example hierarchy gives you an overview of how our DBMSs are structured, although slight variations may occur between products. Most RDBMSs begin with an instance, a single way of organizing the database and everything it contains. Many RDBMSs permit more than one database within a single instance. You will generally find at least one schema at some level in the hierarchy. A schema is a logical grouping of objects within a database. Schemas define how database objects are named and prevent ambiguous references. Some RDBMSs consider the schema a parent object of a database, and others consider it a database object. Within a schema are the database objects, including tables, constraints, and indexes. Now, an instance is a logical boundary for a database or set of databases, where you organize database objects and set configuration parameters. Every database within an instance is assigned a unique name, has its own set of system catalog tables, which keep track of the objects within the database, and has its own configuration files. You can create more than one instance on the same physical server, providing a unique database server environment for each instance. The databases and their objects within one instance are isolated from those in any other instance. You can use multiple instances when you want to use one instance for a development environment and another instance for a production environment, restrict access to sensitive information, or control high-level administrative access. Not all RDBMSs use the concept of instances, often managing database configuration information in a special database instead. In cloud-based RDBMSs, the term instance means a specific running copy of a service. A schema is a specialized database object that provides a way to group other database objects logically. A schema can contain tables, indexes, constraints, and other objects. When you create a database object, you can assign it to a schema. In most RDBMSs, the default schema is the user schema for the currently logged-on user. Many RDBMSs use a specialized schema to hold configuration information and metadata about a particular database. For example, tables in a system schema can store lists of database users and their access permissions, information about the indexes on tables, details of any database partitions that exist, and user-defined database types. Database objects are the items that exist within the database. The process of database design includes defining database objects and their relationships with each other. You can create and manage database objects through graphical database management tools, scripting, or accessing the database through an API. If you use SQL to create or manage the object, you will use data definition language statements like create or alter. In most RDBMSs, you can create objects such as tables, logical structures consisting of rows and columns which store data. Constraints. Within any business, data is often subject to certain restrictions or rules. For example, an employee number must be unique. Constraints provide a way to enforce such rules. Indexes. An index is a set of pointers used to improve performance and ensure the uniqueness of the data. Keys. A key uniquely identifies a row in a table. Keys enable DBAs to define the relationships between tables. Views. A view provides a different way of representing the data in one or more tables. A view is not an actual table and requires no permanent storage. Aliases. An alias is an alternative name for an object, such as a table. DBAs use aliases to provide shorter, simpler names to reference objects. Events. An event is a data manipulation language, DML, or data definition language, DDL, action on a database object that can initiate a trigger. Triggers. A trigger defines a set of actions performed in response to an insert, update, or delete on a specified table. And finally, log files. Log files store information about transactions in a database. In this video, you learned that an instance is a logical boundary for a database or set of databases where you organize database objects and set configuration parameters. A schema is a specialized database object that provides a way to group other database objects logically. Schemas also provide a naming context for database objects. And database objects are the items that exist within the database, such as tables, constraints, indexes, keys, views, aliases, triggers, events, and log files. Welcome to System Objects and Database Configuration. After watching this video, you will be able to describe the purpose of system objects, recognize different types of system objects, describe how to use configuration files, explain common configuration settings, and describe how to configure on-premises and cloud databases. Whether trying to find out if new indexes are helpful, the transaction count on a database at a specific time, or who's connected to the database at any given time, data that allows you to know how your databases are performing is crucial. RDBMSs store information about their databases, known as metadata, in special databases, schemas, or catalogs. They store specific types of information about the database, such as the name of the database or table, the data type of a column, or access privileges, known as metadata. Other terms used for this information store are data dictionary and system catalog. The RDBMS controls and updates the system objects, but you can query the metadata tables to discover information about the objects in the database. Different RDBMSs use different names for their metadata stores. DB2 uses the catalog and the directory. The catalog consists of tables of data about everything defined to the DB2 system. When a user creates, alters, or drops any object, DB2 inserts, updates, or deletes rows of the catalog that describe that object and how it relates to other objects. The directory contains the DB2 internal control data used by DB2 during its normal operation. Among other things, the directory contains database descriptors, access paths for applications, and recovery and utility status information. MySQL uses a system schema to store database metadata. For example, each new MySQL instance has 4 system databases: information_schema, MySQL, performance_schema, and sys. Each system database contains several read-only tables. PostgreSQL uses the system catalog, which is a schema with tables and views that contain metadata about all the other objects in the database and more. With it, you can discover when various operations happen, how tables or indexes are accessed, and whether the database system is reading information from memory or needing to fetch data from disk. During any database installation, you supply parameters like the location of the data directory, the port number that the service listens on for connections, memory allocation, and much more. You can accept the default options or supply custom values to suit the environment. The database installation process saves this information into files known as configuration or initialization files. The database uses the information in these files to set parameters as it starts up. Again, different RDBMSs use different files, file locations, and settings. Still, they all serve the same purpose: to provide the initial configuration information for the database as it starts up and operates. Configuration information can include general settings, like the location of data and log files, and the port the server listens on for requests. Or configuration information can be more focused, like settings that affect performance, including memory allocation, a connection timeout, and the maximum packet size. To store configuration information, DB2 uses the SQL-dbconf file. MySQL uses my.ini files on Windows-based systems and my.cnf files on Linux-based systems. and PostgreSQL uses the postgresql.conf file. Now, suppose you want to modify these parameters after the database has started. In an on-premises RDBMS, you stop the database service, modify the file, and then restart the service, causing the database to read the modified settings. In a cloud-based RDBMS, you select configuration options as you create the database. One advantage of cloud-based systems is that you can scale many configuration options, such as storage size and compute power, through a graphical interface as the service is running. You don't have to edit configuration files. In this video, you learned that system objects store database metadata. You can query these objects to get information about the configuration and performance of your database. Different RDBMSs use different names for their system objects. Most use the terms system schema, system tables, catalog, or directory. Configuration files store the information that the database needs as it initializes. And again, different RDBMSs use different names for their configuration files, like SQLDBconf, my.ini, or PostgreSQL.conf. In an on-premises RDBMS, you edit the configuration file to change a setting. And in a cloud-based RDBMS, you can scale settings dynamically. Welcome to Database Storage. After watching this video, you will be able to differentiate between physical and logical storage, describe table spaces and explain their benefits, describe storage groups and their function, and identify when to use partitions. As a DBA, you'll be responsible for ensuring that your database has enough storage space for all the data that it needs to store. You must determine the capacity required for the database and plan for growth. In cloud-based databases, expanding your storage space is performed through an API or a graphical console. One of the advantages of using a cloud-based database is that it is so easy to scale up and scale down in terms of storage space. In a self-managed or on-premises environment, you can also plan storage space for improved performance, storing competing resources on different disks. RDBMSs separate the physical storage of data files on disk from the logical design of the database, allowing more flexibility in managing the data files. You can manage the data through a logical object without being concerned about the nature of the physical storage. For example, you can issue a command to back up a database without having to specify all the physical disks that store the database. Table spaces are structures that contain database objects, such as tables, indexes, large objects, and long data. DBAs use table spaces to logically organize database objects based on where their data is stored. Table spaces define the mapping between logical database objects and the physical storage containers that house the data for these objects. A storage container can be a data file, a directory, or a raw device. Table spaces contain one or more database objects. In this example, tablespace 1 contains multiple small tables, whereas tablespace 2 only houses a single large table, and tablespace 3 contains frequently used indexes. DBAs configure one or more storage containers to store each table space. In this example, container 1 stores tablespace 1, containers 2 and 3 store tablespace 2, and container 4 stores tablespace 4. By using the combination of table spaces and containers, you can keep logical database storage separate from physical storage and manage the disk layout of a database and its objects. This results in several benefits. Performance. You can use table spaces to optimize performance. For example, you can place a heavily used index on a fast SSD. Alternatively, you can store tables containing rarely accessed or archived data on a less expensive but slower magnetic hard drive. Recoverability. Table spaces make backup and restore operations more convenient. Using a single command, you can make a backup or restore all the database objects without worrying about which storage container each object or table space is stored on. and storage management. The RDBMS creates and extends the data files or containers depending on the need. When necessary, you can also manually expand the storage space by adding another storage path or container to the table space. Some RDBMSs provide storage groups. A storage group is a grouping of storage paths or containers based on similar performance characteristics. This allows you to perform multi-temperature data management more easily. In this context, temperature refers to the frequency of data access. Hot data is accessed very frequently, warm data is accessed somewhat frequently, and cold data is accessed infrequently. By using storage groups, you can organize your data and storage based on temperature. In this example, very frequently accessed hot tables can be placed in tablespace H, which is distributed on a group of fast storage devices. Somewhat frequently accessed tables in tablespaces W1 and W2 can be stored on a warm storage group. And the least frequently accessed tables in tablespace C can be stored on slower and less expensive storage devices in a cold group. Using storage groups helps with optimizing performance for frequently accessed data and reducing costs for storing infrequently accessed data. A partitioned relational database is a relational database whose data is managed across multiple database partitions. You can partition tables that need to contain very large quantities of data into multiple logical partitions, with each partition containing a subset of the overall data. Database partitioning is used in scenarios that involve very large volumes of data, such as data warehousing and data analysis for business intelligence. In this video, you learned that database storage is managed through logical database objects and physical disk files. Tablespaces are structures that organize database objects based on where their data is stored. Storage groups are groupings of storage paths or containers based on similar performance characteristics. And partitions store subsets of data from a very large database to improve performance. Welcome to Introduction to Backup and Restore. After watching this video, you will be able to describe common backup and restore scenarios, explain the difference between physical and logical backup, list the objects that you can backup and restore, and explain what you need to consider when backing up databases and their objects. Backup and restore is a common phrase in database conversations and often used to refer to the process of backing up data for protection purposes, restoring it after data loss from an unplanned shutdown, accidental deletion, or data corruption. However, there are other scenarios when you might want to backup or restore your databases or objects within them. As a data engineer, you are likely to perform data backup and restore operations to transfer data from one database to another. This may be to facilitate a change of RDBMS, to share data with or load data from a business partner, or to create a copy of the data for use in another location or system, such as development or test. When backing up databases, you can perform either logical or physical backups. A logical backup creates a file containing DDL, such as create table, and DML commands, such as insert, that recreate the objects and data in the database. As such, you can use this file to recreate the database on the same or another system. Generally, when you perform a logical backup and restore, you reclaim any wasted space from the original database because the restore process creates a clean version of the tables. Generating logical backups can take a long time for large databases and may impact the performance of other queries that are concurrently running. Logical backups enable you to backup granular objects. For example, you can backup an individual database or table. You typically use backup, restore, import, export, dump, and load utilities to perform logical backups. A physical or raw backup creates a copy of all the physical storage files and directories that belong to a table, database, or other objects, including the data files, configuration files, and log files to aid point-in-time recovery. Physical backups are often smaller and quicker than logical backups. They are useful for large or important databases that require fast recovery times. They are similar to backing up any other types of files on your physical system. However, this means you won't be able to easily recover individual tables or database objects if a physical file contains data from more than one object. Because the backup file is specific to the RDBMS, you can only restore it to a similar system. This approach of taking storage-level snapshots is common for databases utilizing specialized storage systems and on cloud. You can choose exactly which parts of a database you want to back up. Depending on the RDBMS you are using and type of backup you are performing, you can back up as a whole database, the contents of a schema, one or more tables from a database, a subset of data from one or more tables in a database, or a collection of other objects in the database. And because you can also choose the regularity and type of backup you perform, you can customize your backup policies to exactly meet your needs. When using backup and restore, you should remember to check that your backup file or files are valid and that you can use your restore plan to restore them successfully. It is essential to check these when using backup and restore as part of your disaster recovery plans, as an invalid backup or an inability to restore can result in data loss. You should also ensure that you secure the transfer and storage location of your backup files at the same level that you secure the data in your database. When performing backups, some RDBMSs support additional options that you can use. You may be able to configure a compression level for the backup files. Compressing the files will reduce the output file size, which can be useful for large databases, or if you are packing up to a remote location. However, it comes at a cost of time taken to perform the backup and the restore procedures. You may also be able to encrypt the backup files to reduce the risk of any data being compromised. But again, this will increase the time taken for the backup and restore. In this video, you learned that you can use backup and restore for data recovery and other purposes. Physical backups create a copy of the raw database storage files and directories, whereas logical backups extract the data from a database and save it in a special format. You can back up whole databases or objects within them. You should always check that your backup is safe and usable and that your restore plan works. And you can use backup options to compress or encrypt your files. Welcome to Types of Backup. After watching this video, you will be able to identify common types of database backup and describe the advantages and disadvantages of different types of database backup. There are many different types of backup that you can use to meet your backup and restore needs. The choice of which are available to you depends on the database system that you are using. The commonly used types include full backup, point-in-time backup, differential backup, and incremental backup. A full backup is a complete copy of all the data in the object or objects that you are backing up. Performing full backup simplifies the restore and recovery processes because you just need to locate the latest full backup and restore that one file. However, as the size of your database increases, the time, bandwidth, and storage for the backup file also increases. If you decide to keep previous copies of the backup for safety, you will be storing many instances of a large file. However, if you only want one copy, you must accept the risk that if the backup file is corrupt, you cannot restore your data. Also consider that if only a subset of your data is regularly changing, you could be needlessly backing up the same data many times. Storing a complete copy of your data outside of the RDBMS means that you must ensure it is adequately secured and that it cannot be accessed by unauthorized users. When you restore a full backup, you restore the data to the state that it was in when the backup was taken. But the database may have processed many transactions since that time, which should ideally be restored too. One way around this issue is to enable logging of each transaction on your database, and then you can use the information in the log file to reapply the transactions to the restore database. The process of reapplying transactions after restoring a database backup is known as recovery. It enables you to recover the data to a state that it was in at a particular time, hence the name point-in-time recovery. For example, if you know that a DML statement run at 11:05 a.m. erroneously deleted some data, you can restore the latest full backup, then reapply the transactions up to that point in time, minimizing the loss of data changes that occurred between the last full backup and the moment that the wrong data was deleted. Different database systems use different terminology for the log containing the transaction information. For example, MySQL calls it the binary log, Postgres calls it the write-ahead log, and DB2 on Cloud calls it the transaction log. Because full backups can require a lot of time, bandwidth, and storage, one alternative is to use them in conjunction with differential backups. A differential backup consists of a copy of any data that has changed since the last full backup was taken. This makes the differential backup file much smaller than the full backup file, reducing the time, bandwidth, and storage needs for the backup, while still enabling you to restore a recent copy of the data. For example, you could perform a full backup once a week on a Sunday, then run a differential backup every day of the week. Each differential backup contains all the changes since the full backup was taken on the Sunday. So, if you need to restore the database on a Tuesday, you first restore the full backup from Sunday, then restore the differential backup from Tuesday. You do not need to restore Monday's differential backup because all the changes in that file are also included in the differential backup from Tuesday. Restoring data from full and differential backups will take longer than simply restoring a full backup. But because you restore data less frequently than you back it up, you are likely to save time overall. Incremental backups are similar to differential backups, but they can only contain data that has changed since the last backup of any type was taken. For example, you could perform a full backup once a week on a Sunday, then run an incremental backup every day of the week. Each incremental backup only contains changes since the backup was taken on the previous day. So if you need to restore the database on a Tuesday, you first restore the full backup from Sunday, then the incremental backup from Monday, and then the incremental backup from Tuesday. Restoring data from full and incremental backups will take longer than simply restoring a full backup or restoring differential backups. But the time taken to perform the incremental backups is likely to be less than needed for a differential backup. In this video, you learned that full backups are simple to create and restore, but can be slow to run and result in large files. Point-in-time recovery provides a more granular recovery model than just using full database backups. Differential backups are quicker to run than full backups, but the restore process can take longer. And incremental backups are even quicker to run, but the restore process can take longer still. Welcome to Backup Policies. After watching this video, you will be able to explain the difference between hot and cold backups and determine an appropriate backup policy. Hot backups, or online backups, are those performed on data when it is in use. The advantage of hot backups is that they have no impact on availability, and users can continue with their activities throughout the backup period. However, hot backups can result in performance degradation for users while the backup is running, and can impact data integrity if data changes during the backup process. The alternative to hot backups is to take the database offline while the backup is run. This is known as a cold or offline backups. This eliminates the data integrity risks associated with hot backups, but has a greater impact on user availability and cannot be used in 24/7 environments. Hot backups are generally stored on an available server and often receive regular updates from the production database. This enables them to be brought online should the production server fail to ensure continuing availability to users. Cold backups tend to be stored on external drives or on servers that are shut down between backup operations. This can provide greater data safety, but does mean that the recovery process will take longer than that of a hot backup. You have already seen that there are many decisions that you must make about how to implement your backup and restore policy. Physical or logical backups, type of backup, hot or cold backup, compression, and encryption. You also need to consider how often you need to back up your data. This is dependent on the impact that any data loss would have on your business operations and how frequently your data is changing. For example, a table containing product information is likely to change less frequently than a table containing customer orders, so you could back that up less regularly than the orders table. But if your orders table already contains a large amount of data, you won't want to be performing frequent full backups, so you should consider using differential or incremental backups for it. You also need to consider when to perform your backups. If your data is mainly accessed during the working day in one time zone, you should schedule your backup outside of those hours. However, if it is accessed across the whole day, you could consider implementing full backups at the weekend and incremental or differential backups on a daily basis. Because backups will be a regular task, if your RDBMS provides the availability to schedule or automate your backups, you should consider using it. It is equally important to consider backing up your cloud databases. Depending on the RDBMS that you are using, backups might run automatically. You may need to enable automated backups. You may need to run manual backups. Or you may be able to use the techniques that you have learned about in this video to run your own backup strategy. For example, the paid plans of DB2 on Cloud run an encrypted backup every day and with the Enterprise or Standard plans. You can also run manual backups and perform point-in-time restores. And when using Google Cloud SQL for MySQL, Postgres, and SQL Server, you can enable automated incremental backups or perform on-demand backups. If you find your combination of RDBMS and cloud provider does not support any of these options, there are third-party backup tools available to purchase. In this video, you learned that hot or online backups allow data to be backed up while the database is active, whereas cold backups require the database to be offline. Your backup policy should be determined from your recovery and availability needs and your data usage patterns. And most managed cloud databases provide automated backup functionality with some configurable options. Welcome to using database transaction logs for recovery. After watching this video, you will be able to describe database transaction logs. Explain the primary uses of transaction logs, indicate where transactional logs are stored and how to access them, and identify the typical structure of a transactional log. Separate from the diagnostic log, a database management system, or DBMS, uses transaction logs to keep track of all transactions that change or modify the database. The information stored in these transaction logs can be used for recovery purposes when data is accidentally deleted or a system or hardware failure, such as a disk crash, occurs. In case of such events, the transaction log, in conjunction with a database backup, can help restore your database back to a consistent state at a specific point in time. For example, in this timeline, at time T1, you issue the backup command to make a full copy of your database. Users then continue working, and the information about their activities is kept in transaction logs. At time T2, there is a problem that damages the database. So at time T3, you issue a restore command using the backup image you took at time T1. This allows you to get the database back to the point in time that the backup was taken. Then, at time T4, you apply the transaction logs for a period of time between T1 and T2 to the restored database. This process of applying committed transactions from transaction logs is called roll-forward recovery, and it returns your database to the point just before the crash happened. You typically specify where you want transaction log files to be stored using the database configuration. Here's an example location of a DB2 transaction log file directory in an SQLogdir subdirectory on a Windows system. In PostgreSQL, the log files default to being stored in the pgxlog subdirectory. In PostgreSQL, the transaction log file is referred to as a write-ahead log, or WAL, because before the database manager writes the database changes or transactions to data files, the DBMS first writes them to the WAL. A recommended best practice, at least for production databases, is to place the transaction log files on storage volumes that are separate from where the database objects, like table spaces, are stored. This not only helps with performance, so database writes are not competing with log writes, but also improves recoverability since it isolates logs from crashes or the corruption of data volumes. For even more enhanced recoverability in business-critical databases, some relational database management systems, or RDBMSs, provide the ability to automatically mirror logs to a second set of storage devices. Or you can write scripts to copy or ship logs to remote replicas or standby systems in a process called log shipping. In many RDBMSs, like DB2 and SQL Server, transaction logging is enabled by default, but you still may want to change the default settings for improved recoverability and performance. In other RDBMSs, like MySQL, transaction logging is disabled by default and may need to be manually configured. For MySQL, you can run the show binary logs command to check if logging is enabled, and if it is, you will see a list of the log files. Unlike other types of logs, such as diagnostic and error logs that are mostly in text format and human-readable, the database transaction logs are typically in binary formats that are sometimes encrypted and require specialized tools to format and display contents. For example, in MySQL, you use the MySQL binlog tool to view the contents of MySQL transaction log files, also known as binary logs. The sample output shows a log file entry for an insert statement. And for DB2, you use the DB2 FMT log tool for formatting and displaying log file information. The sample output shows a record for a DDL statement to create a table. A log file contains multiple entries, and the information they contain may vary depending on the RDBMS. For example, a typical database log record in DB2 is made up of a log transaction ID number, which is a unique ID for the log record, the database record type, which describes the type of database log record, a log sequence number, which is a reference to the database transaction generating the log record. A previous log sequence number is a link to the last log record. This implies that database logs are constructed in linked list form, and information which details the actual changes that triggered the log record to be written. In this video, you learned that database transaction logs keep track of all activities that change the database structure and record transactions that insert, update, or delete data in the database. Transaction logs assist with recovery of databases in case of a system failure, disk corruption, or accidental deletion. By applying or replaying transactions in the log, the database can be recovered or rolled forward to a point in time before a data catastrophic event. A good practice is to store log files in a location separate from database volumes by changing default settings in the database configuration. And the format of transaction logs varies by RDBMS, but each log entry typically contains a log record ID and details about the database activity or transaction that modified the database. Welcome to the overview of database security. After watching this video, you will be able to describe different levels of database security, explain the difference between authentication and authorization, identify the granularity of security on objects in a database, and describe how auditing, encryption, and application security can enhance your database security. Ensuring the security of the data stored in your systems is an essential part of the database management role. It involves identifying the potential risks to your data and mitigating those risks by applying security measures and controls at all levels of a system. Even though the actual implementation of the measures at some levels may not be your direct responsibility, it is imperative that you evaluate that they are adequate for the data you store or access there. First, you need to make sure that the actual servers in your system are physically secure. For on-premise servers, you should assess who has access to server location and the security measures in place. If you are using a managed cloud environment, your provider will be responsible for the security at this level. Next, you should consider the operating system hosting your database. You should ensure that it is regularly patched with the latest tested updates, that it is hardened using a known configuration to reduce vulnerabilities, and that it is continuously monitored for any unauthorized access. You should take similar measures on your RDBMS to those for your operating system. You should regularly apply the latest tested updates. You should review and use all security features and configuration options available in the system. And also, you should ensure that only a small set of trusted users have administrative privileges. Users and client applications need to be permitted to access a server or database and the objects in it. First, users need to be authenticated on the server or database to enable them to access it. And then they need to be granted permissions on individual objects or groups of objects in the database to interact with them. Database authentication is similar to the authentication you use when using a PIN or fingerprint to access your cell phone or a password to access your computer. It is a process of verifying that the user is who they claim to be, for example, by validating credentials such as username and password. Some database systems enable you to use operating system or other credentials to authenticate against a database. For example, you can use external authentication methods, such as Pluggable Authentication Module, or PAM, Windows Login IDs, Lightweight Directory Access Protocol, LDAP, or Kerberos. Even when a user is authenticated on a database, they still need to be authorized to access the objects and data in the database. You authorize users by giving them permissions or privileges to access objects and data. Because groups of users often need the same access privileges, in most RDBMSs, you can grant privileges to a group of users who undertake a specific role in that database. Assigning privileges will vary depending on the object you are working with. For example, on a table, you can allow users to select, insert, update, or delete data, or to alter the structure of the table. In some RDBMSs, you can narrow this down even further to assign privileges on a columnar basis. You should always use the principle of least privilege. That is, only allow users to access the least amount of data that they need to succeed in their tasks. In addition to restricting users to only access the information and objects that their role requires, you should also consider monitoring and auditing database activity. You should track which users access a server or database and the actions that they perform. Analyzing this information against your security plan can alert you to gaps in it. As well as securing your systems and data and auditing access to it, you could consider using encryption to add another layer to your security system. If an intruder does manage to access the data, they also have to decrypt the data to make any use of it. Certain industry regulations and regions legislate the use of specific levels of encryption for sensitive data. It is important to check such regulations for algorithm and key management requirements when planning your database security. Do remember, though, that encrypting and decrypting data can be a time and resource-intensive operation. So you will need to consider the impact this will have on your operations and whether you need to upgrade your hardware accordingly. Even the most secure combination of operating system and RDBMS can be compromised by lax application security, such as SQL injection strings and insecure code. Therefore, it is important that you test and monitor the security of any applications interacting with your data and databases. In this video, you learned that when securing a database, you need to consider the security of the server and operating system as well as the database and data. Users need to be authenticated on the server or database to access it. Users need to be authorized, that is, given permissions or privileges to access the objects and data in the database. You should use the principle of least privilege to reduce access to data. Monitoring and auditing database activity can alert you to threats and security gaps. Encryption can strengthen your data security by making it harder to read any compromised data. And data security includes securing your applications. Welcome to Users, Groups, and Roles. After watching this video, you will be able to describe users, groups, and roles, explain how users, groups, and roles work together, and manage database security objects. A database user is a user account that is allowed to access specified database objects. Depending on the DBMS and your security policies, a user might be explicitly created and authenticated within the database system, or may be created externally and authenticated using external authentication, such as the operating system, or external identity management services like Kerberos, LDAP, and Cloud IAM. When you first create a user, they will generally have few, if any, permissions to actually interact with the database objects, unless they are a creator of the database. Usernames are stored in system tables or catalog tables, which you should not try to edit directly. All RDBMSs will provide SQL commands and/or user interface tools that you can use to manage your users. Some RDBMSs support the concept of user groups. In some cases, such as Postgres, you define groups in the database, and they are logical groupings of users to simplify user management. In other systems, such as SQL Server and DB2, you can map a database group to an administrative group in the underlying operating system. This is particularly useful when you are using that operating system to authenticate your users. Similarly, if you are running your database on Amazon Relational Database Service, or RDS for example, you can use Virtual Private Cloud or VPC security groups and Database or DB security groups to manage your user access. Database roles are similar to database groups in that they confer privileges and access rights to all users of that role. A database role defines a set of permissions needed to undertake a specific role in the database. For example, a backup operator role would have permissions to access a database and to perform backup functions. Some RDBMSs have a set of predefined roles that you can use for your users, such as a database owner or backup operator role. And most enable you to create your own roles, so you might create a salesperson role that has the permissions a salesperson will need on the relevant tables in the database. Assigning privileges to groups or roles rather than individual users greatly simplifies your security management tasks. If you know that a set of users all need access to the same functionality to fulfill their job role, you can put those users in one group and assign the relevant permissions to the group. If the job role changes in the future, it is quicker, easier, and less prone to mistakes to just add the new permissions to the group rather than individual users. Similarly, if a new member of staff joins the team, you can simply add them to the role or group rather than having to assign all the separate permissions to them. One user can be a member of one or more roles. So, the head of the sales group could be a member of the group head's role and the salesperson role. When implementing role or group membership, remember to use the principle of least privilege. Only adding users to groups they need to be a member of and ensuring that your roles don't include any permissions that the majority of users in them will not need. In the later scenario, you should reassess your role permissions and create multiple, more granular roles or groups. In this video, you learned that depending on the database, you can create and authenticate users directly in the database system or use external authentication, such as the operating system. In some systems, you define groups in the database to manage users, and in others, you can map database groups to operating system groups. You can use predefined database roles to assign privileges to common sets of database users. You can define custom roles for your own requirements. And groups and roles simplify user management. Welcome to managing access to databases and their objects. After watching this video, you will be able to grant access to objects in a database, revoke access to objects in a database, and deny access to objects in a database. After a user is authenticated on a database, they need permissions or privileges to access the objects and data in that database. Privileges are granted to users and to groups or roles. The combination of a user's own personal permissions and those of the groups or roles they belong to defines their overall permissions. In this video, you will see examples of generic SQL statements. The RDBMS that you are using may use slightly different syntax to the example shown here, and is also likely to provide a graphical interface option to perform these tasks. In systems where users are authenticated outside the database, such as on the operating system or through an external plugin, you may also need to grant them access to the databases they will be working with. You can use the SQL grant connect command to grant connection access to a particular database to a particular user, group, or role. To grant connection access to an individual user rather than a group or role, you simply specify the username in place of the group name. If your RDBMS provides a guest or public account, you may find that by default it has connect privileges to all databases. In this scenario, it is a good practice to revoke that permission so that you ensure only users given explicit permission can access your data. You use the SQL grant command to grant privileges on tables in a database. In this example, the sales team group is granted select privileges on the MyTable table in the MyDB database. You can use similar statements to enable users to insert, update, and delete data by granting them the relevant privileges on a table or tables. To provide these privileges to an individual user, just replace the sales team group name with the name of that user. You can also use the grant statement to grant privileges to create objects in a database. This example shows how to enable a group or role to create a table. And again, you can use a similar statement to enable a user to create an object such as a table or stored procedure. On a procedure or function, you can permit a user or group to view the code. This means that they can view the definition of that function or procedure, but they will not be able to run it or change it. To run the code, a user needs the execute permission, and to change the definition of a procedure, a user needs the alter permission. As well as granting privileges, at times you may want to remove them. You can use the revoke statement to remove granted privileges, and most RDBMSs will also provide revoke functionality in the user interface. However, because an individual's privileges are a combination of those granted to all the groups or roles they belong to, a member of the sales team role may still be able to access this table through their membership of another role. If you want to ensure that users do not have permission for a certain object or action, you can use the deny statement to override any previous grant of that permission. In this video, you learned that you grant permissions to users, groups, or roles. Permissions control access to databases and the objects in them. The range of permissions, from select to insert, update, delete, create, alter, and drop for different types of object, allow for fine-tuning of access for users, groups, and roles. You can revoke a previously granted permission, and you deny a permission to override an existing granted permission. Welcome to Auditing Database Activity. After watching this video, you will be able to explain why auditing is important, describe how to audit database access, and describe how to audit database activity. Auditing or monitoring database activity is a key part of any security plan. Even though auditing doesn't directly protect the database, it can help you to identify gaps in your security system and to track errors in privilege administration. In some industries and countries, it is even a requirement to audit access to sensitive data. You should consider implementing auditing in all your database solutions, whether they be on-premise or in the cloud. Auditing a database involves recording the access and the activity of database users on your database objects. By reviewing such records, also known as logs, you can identify suspicious activity and quickly respond to any security threats you find. If an unauthorized user accesses your database, they have already overcome one or more of the levels of security in your system. Therefore, it is imperative that you track who accesses your database and review the information to identify any unauthorized users. You should also track failed attempts to access the database, as these can help you to identify potential attacks such as brute force attempts on your system. Most database systems provide functionality that you can use to audit database access. For example, in DB2 on Cloud, you can use the user validation category of the built-in audit facility to log user authentication events. In MySQL, the audit log plugin tracks connect and disconnect events. Sometimes authorized users may find that they can view and edit data that they should not have permissions on. If you track all user activity, you can then use the output reports to review which users are accessing which tables and check whether those actions match your security plans. To audit database activity, some RDBMSs use triggers. These are special stored procedures that automatically log the activity after a DML statement event, such as an insert occurs. Other systems enable you to attach actions to the events that occur in the database. In DB2 on Cloud, you can use the Change History Event Monitor to enable auditing on specific tables or objects. And in Postgres, you can use the downloadable PG Audit tool to log individual action types or all actions in a database. You should ensure that whatever auditing implementation you use meets the compliance requirements of your customer or region. In this video, you learned that auditing does not directly protect your database, but does identify gaps in your security. Some industries, customers, or regions may require that audit logs are created and retained. You should audit both successful and failed attempts to access your database. And you should audit and review all activity in your database. Welcome to Encrypting Data. After watching this video, you will be able to explain the advantages of encrypting data, describe the encryption algorithms and keys, identify the differences between symmetric and asymmetric encryption, explain transparent data encryption, explain customer-managed keys, list encryption versus performance trade-offs, and describe how RDBMSs can encrypt data in transit. Data encryption provides yet another layer in your security system and is often the last line of defense if data is compromised. It can help to protect your data at rest and during transmission. Some industries, such as financial and medical services, regions, or specific customers may also require that you encrypt certain types of data. For example, the Payment Card Industry Data Security Standard, or PCI DSS, requires that all companies that process, transmit, or store credit card information encrypt that data. At-rest data refers to your data when it is stored or at rest in your RDBMS. It is important to encrypt data at rest to ensure that malicious users cannot directly access the data files, bypassing your database security measures. Some RDBMSs provide database-level encryption for the entire database. This is often termed Transparent Data Encryption, or TDE. Some provide table or tablespace encryption for individual tables, and some provide column level for maximum granularity and flexibility. Do note, though, that the flexibility that column-level encryption provides is counteracted by performance degradation and complexity of setup. You encrypt data by using an algorithm to change the data into an unreadable string, commonly known as ciphertext. These algorithms use a key to ensure that anyone trying to decipher the text cannot do so without the key. The simplest form of encryption is symmetric encryption, where the same key is used to encrypt and decrypt the data. Mechanisms such as Data Encryption Standard, or DES, and Advanced Encryption Standard, or AES, use symmetric keys. When using only one key, it must be shared between all parties wanting to access that data so that they can all decrypt it. Sharing a key increases the likelihood of it being compromised, and if the key to the encryption is compromised, your data is effectively compromised. Alternatively, some databases use asymmetric encryption, also known as public key encryption. This uses two keys, a public key and a private key known as a key pair. You encrypt the data with the public key, and valid users have a unique matching private key to decrypt it. Rivest-Shamir-Adleman, or RSA, and elliptic curve cryptography, or ECC, are both examples of asymmetric encryption. Because asymmetric encryption involves the use of multiple private keys, it is essential that those keys are held securely. Most modern databases take care of the complexity of encryption and key management for you. Many of them support transparent data encryption, or TDE. The transparent part of its name alludes to the fact that the encryption and decryption is not visible to your users. The database engine encrypts the data before storing it, and then decrypts it when the authorized user or application requests information. Because the database engine is performing the encryption tasks, it also encrypts your database backups too. Although TDE simplifies the process of encrypting your database, you may have concerns about storing data in the cloud and relinquishing the key management process to a third party. Some cloud databases support customer-managed keys, also known as the Bring Your Own Key, or BYOK protocol. This provides a separation of responsibility so that your cloud database system is responsible for the encryption process, but you retain control of the keys that it uses. BYOK provides an extra level of protection by ensuring that the cloud platform storing and encrypting your data does not have access to the decryption keys, so it cannot access your confidential data. It also enables your security admins to manage your corporate keys, while your database admins can continue to manage the data. And for businesses whose customers require regulatory compliance around key rotation and expiration, you have complete control over the keys and their life cycle. Some RDBMSs support both symmetric and asymmetric encryption and enable you to configure which to use. Because of the time and effort it takes the algorithm to process the data, any type of encryption and decryption will decrease the performance of your database. Because asymmetric algorithms generally use longer keys, they tend to have greater performance impact than symmetric algorithms. Therefore, unless you specifically require asymmetric encryption, it is often best to use the symmetric algorithms such as AES and DES. In fact, AES is the recommended method for the earlier PCI DSS credit card example. As well as encrypting data at rest, you should also consider encrypting it in transit. That is, when it is being transmitted across networks or the Internet. As with data at rest encryption, many RDBMSs provide this functionality for you. Some cloud databases encrypt data in transit using Transport Layer Security, or TLS, protocol, while others use Secure Sockets Layer, or SSL, protocol. Some will encrypt your data by default, while others use a configuration setting that you can enable and disable. And similarly to at-rest encryption, encrypting data in transit will affect the overall performance of your system. In this video, you learned that data encryption helps make any data that is compromised unusable. You can encrypt data at rest or in transit. You use algorithms to encrypt and decrypt data. Symmetric encryption is easier to use, but less secure than asymmetric encryption. TDE can simplify encryption setup. Encryption decreases database and transport performance. And you can use TLS and SSL to protect data in transit. Welcome to Overview of Database Monitoring. After watching this video, you will be able to explain why proactive monitoring is important, identify what baseline data you should create, and describe the options available for monitoring database usage and performance. For many database admins, one of the most challenging and necessary elements of database management is performance tuning, and one of the critical parts of this process is database monitoring. The term database monitoring refers to the different tasks related to the scrutinization of the day-to-day operational status of your database. Database monitoring is crucial to maintain the health and performance of your relational database management system, regardless of which vendor's database product you are using. When you perform regular database monitoring, it helps to identify issues in a timely manner so that you can maintain the health and accessibility of your database system. If you do not perform this monitoring function, then problems and outages in your database might go undetected until it's too late. This can cause your users and customers to lose confidence in your service, and potentially your organization could lose customers and income because of it. Most relational database management systems offer tools that enable you to observe the current state of your databases and to track their performance as circumstances vary over time. As a database admin, you can then utilize this information to perform several database monitoring tasks, including forecasting your future hardware requirements based on database usage patterns, analyzing the performance of individual applications or database queries, tracking the usage of indexes and tables, determining the root cause of any system performance degradation, optimizing database elements to provide the best possible performance, and assessing the impact of any optimization activities. Before we can talk about the importance of proactive monitoring, we need to differentiate it from reactive monitoring. Reactive monitoring is done after an issue occurs, when you act in direct response to that issue, perhaps by fixing a configuration setting or adding more resources, for example. The most common situations when reactive monitoring occurs is either when your database security has been breached, or the performance of your database reaches critically low levels, or when some other kind of major database incident occurs that greatly impacts your business and therefore needs resolving as soon as possible. In contrast, a proactive monitoring strategy seeks to prevent this reactive panic by identifying issues before they grow into large problems. This is primarily achieved by observing specific metrics from your database, then sending alerts to interested parties if the values of these metrics reach abnormal levels. Proactive monitoring typically utilizes automated processes to perform tasks such as regularly verifying that a database system is online and accessible, verifying that configuration changes do not adversely affect the performance of the database system, and that the database system is operating and performing at acceptable levels. This proactive approach is widely considered to be the better strategy and is preferred by most database admins. To determine whether your database system is performing at its most optimal, you first need to establish a baseline for your database system's performance. To do this, you need to record key performance metrics at regular intervals over a given time period. Once you have established a database system performance baseline, you can then compare these baseline statistics with the performance of your database system at any given time. If your comparison indicates that the current performance measurements are either significantly above or below the performance baseline, then these can become potential targets for further analysis and investigation. From these investigations, you might then determine that some database elements need reconfiguring or optimizing. Even when things are working well and as expected, you can still use your performance baseline data to help you determine operational norms, such as your peak and off-peak hours of operation, typical response times for running queries and processing batch commands, and the time taken to perform database backup and restore operations. The following areas typically have the greatest effect on the performance of your database system: system hardware resources, network architecture, operating system, database applications, and client applications. There are two ways to monitor operations in your database. You can view information that shows the state of the various elements of your database in real time using monitoring table functions. For example, you can use a monitoring table function to examine the total amount of space used in a table. These table functions let you examine monitor elements and metrics that report on virtually all aspects of database operations. The monitoring table functions use a lightweight, high-speed monitoring infrastructure. Alternatively, you can set up event monitors to capture historical information as specific types of database events occur over a given time period. Event monitors capture information about database operations over time as specific types of events occur. For example, you can create an event monitor to capture information about locks and deadlocks as they occur in the system. Or you might create an event monitor to record when a threshold that you specify, for example, the total processor time used by an application or workload, is exceeded. Event monitors generate output in different formats and can write this output to regular tables. Some even have additional output options. In this video, you learned that database monitoring is crucial to maintain the health and performance of your relational database management system. Proactive monitoring seeks to prevent a reactive panic by identifying issues before they grow into larger problems. You need to establish a baseline for your database system's performance to determine whether your database system is performing at its most optimal. And to monitor operations in your database, you can either view the state of various elements of your database at a specific point in time, or you can set up event monitors to capture historical information as specific types of database events occur over time. Welcome to Monitoring Usage and Performance, Part 1. After watching this video, you will be able to explain why you need to monitor at different levels, and describe the 4 levels at which you should monitor. You need to use the appropriate tools to monitor your database and effectively monitor its performance. But regardless of which monitoring tools you use, the relevant information is obtained by using several key performance indicators, or KPIs, which are more commonly referred to as metrics. Database performance is measured by using these key database performance metrics, which enable database admins to effectively optimize their organization's databases for best performance. Apart from monitoring for performance reasons, regular monitoring is also useful for operations, availability, and security purposes. The ultimate goal of monitoring is to identify and prevent issues from adversely affecting database performance. However, some issues that occur may be caused by your hardware, or perhaps your software, or possibly your network connections, or even the queries that you execute or some other unknown factor. The point is, issues can arise in several areas of your database environment. Therefore, to efficiently and successfully monitor the usage and performance of your databases, you need to monitor at several distinct levels within your database environment. The 4 monitoring levels are the infrastructure level, the platform level or instance level, the query level, and the user or session level. So first, there's the infrastructure level. It's vital that all the underlying infrastructure components, such as operating systems, servers, storage hardware resources, and network components be working efficiently under the hood of the database platform and the queries. Next, there's the instance or database platform level. Irrespective of whether you're handling relational database systems such as DB2, PostgreSQL, MySQL, or any other flavor of relational database system for that matter, or if you're managing a combination of more than one of them together, each platform is a consideration in terms of performance. Database monitoring at the platform level is crucial because it offers holistic insight into all the elements necessary to maintain consistent database performance. Next is the query level. Typically, your line of business applications will be repeatedly running queries against your database instances, and then formatting and returning the relevant results of those queries to your users. The majority of bottlenecks that might occur at this level will primarily be due to inefficient query statements that may cause latency, mishandle errors, and diminish query throughput and concurrency. And lastly, we have the user or session level. This level can often be the most misleading monitoring level of them all, because if your users are complaining about something not working, then you can just obtain further information about the issue they are having, investigate it, and hopefully fix it. But what if your users aren't currently complaining about things not working? Can you just assume that everything is running fine, put your feet up, and relax? Unfortunately, no. Just because there may not be an issue right now doesn't mean that there won't be one just around the corner. Truly successful monitoring means constantly monitoring the usage, performance, and behavior of your database system in a proactive and continuous manner. The nirvana of database monitoring is achieved when you proactively identify issues before your users even are aware of them. Monitoring all 4 of these levels is crucial to maintaining service-level agreements, or SLAs, such as high availability, high uptime, and low latency for your databases. In this video, you learned that database performance is measured by using key performance indicators known as metrics. Metrics enable DBAs to optimize organizations' databases for best performance. Successful database performance monitoring means monitoring at multiple levels. And you should monitor at the infrastructure, platform, query, and user levels. Welcome to Monitoring Usage and Performance Part 2. After watching this video, you will be able to describe key database usage and performance metrics, describe the in-product tools available for reviewing metrics, and describe several third-party monitoring tools. Some of the key metrics for monitoring the usage and performance of your database include the following. Database throughput is one of the most significant metrics of database performance. It indicates how much total work is being taken on by your database and is typically measured by the number of queries executed per second. Database resource usage monitors the database resource usage by measuring the CPU, memory, log space, and storage usage. This summary metric represents the database resource usage by 2 aspects: average max latest number and time series number. Database availability signals whether the database is up or down, that is, available or unavailable. It is typically a summary metric that represents the historical data on available time as a percentage. Database responsiveness shows how well the system is responding to inbound requests and is another of the more commonly used database performance metrics. It provides DBAs with information on the average response time per query for their database servers, indicating how quickly they respond with query results. Database contention indicates whether there is any contention between connections by measuring lock weights and concurrent database connections. Database contention is the term used to describe what happens when multiple processes are competing to access the same database resource at the same time. And units of work tracks what transactions or units of work are consuming the most resources on the database server. Here are some more key metrics. Connections can display all kinds of network connection information to a database management console and can indicate whether a database server might fail due to long-running queries or having too many open connections. Database connections are network connections that enable communication between clients and database software. Open connections are used for sending commands and receiving responses in the form of result sets. Most frequent queries tracks the most frequent queries received by your database servers, including their frequency and average latency, that is, how long they take to be processed. It can help DBAs optimize these queries to gain substantial performance improvements. Locked objects shows detailed information about any locked processes and the process that blocked them. Locks and blocks stop several concurrent transactions from accessing an object at the same time. They put contending processes on hold until that object has been released and is accessible again. Stored procedures displays the aggregated execution metrics for procedures, external procedures, compiled functions, external functions, compiled triggers, and anonymous blocks invoked since database activation. Buffer pools tracks the usage of buffer pools and table spaces. A directory server uses buffer pools to store cached data and to improve database performance. When the buffer pool fills up, it removes older and less used data to make room for newer data. And Top Consumers shows the top consumers of a system's resources and can help DBAs with capacity planning and resource placement. Please note, this is just a small selection of the numerous metrics available in most database management systems. To review these key database performance metrics, you will use different out-of-the-box tools depending on your database. For example, in DB2, you can use tools such as the DB2 Data Management Console, the Workload Manager, and Snapshot Monitors. In PostgreSQL, you can use the PG Admin Dashboard, which is a very popular open-source query monitoring tool for PostgreSQL systems. In MySQL, you can utilize the Performance Dashboard, Performance Reports, and Query Statistics tools in the MySQL Workbench, and you can use the MySQL Query Profiler to identify slow-running queries. There are several third-party performance and query monitoring tools available to help you monitor queries, optimize performance, and speed up your database. Some of them may also provide performance tuning and query optimization capabilities as well. For PostgreSQL systems, there is the PG Analyze tool, which provides automatic insights into query plans, query analysis, database visualization and dashboards, log insights, and performance optimization and monitoring. And if you have a PostgreSQL, MySQL, SQL Server, or Oracle database and need a query monitoring tool, you could try PRTG Network Monitor. Many of the third-party tools are available for multiple database systems, such as SQL Server, Oracle, Sybase, DB2, MySQL, and PostgreSQL, to name but a few. SolarWinds offers a subscription-based monitoring solution called Database Performance Analyzer. Foglight for Databases from Quest enables you to proactively monitor your complete database environment and view the state of all database platforms in a single comprehensive interface. And Datadog is a SaaS platform that includes multiple system monitoring tools. It has more than 450 built-in integrations to connect to multiple different database systems. In this video, you learned that there are many different metrics you can use to monitor the usage and performance of your databases. And there are several different tools available to monitor your databases and queries, some of which are included with your database product, while others are third-party offerings. Welcome to Optimizing Databases. After watching this video, you will be able to describe why you need to optimize your databases, describe the optimize table command for MySQL, describe the vacuum and re-index commands for PostgreSQL, and describe the run stats and reorg commands for DB2. First off, let's ask the obvious question. Why do you need to optimize your databases? Well, over time, as the volume of data stored in your databases increases and the operational workloads increase, data can become fragmented. Tables can be left empty or partially empty, and database performance can suffer. By optimizing your databases, you can identify bottlenecks, fine-tune database queries, and ultimately reduce database response times for your users. Each relational database system has its own utilities or commands for optimizing its databases. For example, for MySQL databases, you can use the optimize table command. For PostgreSQL databases, you can use the vacuum and reindex commands. And in DB2, you can use the run stats and reorg commands. If your MySQL database receives a significant number of insert, update, or delete operations, it can lead to fragmentation of your data files, meaning that a lot of unused space is wasted, which in turn can impact your database's performance. Therefore, it is recommended that database admins defrag their MySQL tables on a regular basis. In MySQL, the optimize table command reorganizes the physical storage of table data and associated index data to reduce storage space and improve input-output efficiency when accessing a table. To use the optimize table command, you need to have select and insert privileges for the tables you are working on. This example would optimize 3 different tables in one operation. You could also use a graphical tool such as PHP MyAdmin to optimize tables in MySQL. The vacuum command can be used on your PostgreSQL database to perform garbage collection and, optionally, analysis tasks. Vacuum reclaims lost storage space consumed by dead tuples, which are not physically removed from their database tables after being deleted or made obsolete by an update during routine PostgreSQL operations. Regularly reclaiming this lost storage space can help improve your database's overall performance in PostgreSQL. Please note that if the auto vacuum feature is enabled, then PostgreSQL will automate the vacuum maintenance process for you. In these examples, when you run vacuum with no parameters, the command will free up space on every table in every database that the current user has the rights to perform this command on. If you specify the name of a table, then the command will only process and free up space on that table. Without the full parameter, the vacuum command can run alongside normal read and write table operations, as it does not require an exclusivity lock, and any reclaimed space is retained for future reuse within the table it was vacuumed from. However, if you specify the full parameter, the command will create a complete copy of the table contents and write it to disk with no unused space, which allows the space to be reclaimed by the operating system. So, using the full parameter can reclaim more space for you, but it takes much longer to run and requires an exclusivity lock on each table while it is being processed. In PostgreSQL, you can use the reindex command to rebuild one or more indexes. Reindex rebuilds an index using the data stored in the index's table and replaces the previous, older version of the index. It can be used when software bugs or hardware failures have corrupted an index, or when an index has become bloated and contains numerous empty or nearly empty pages. You need to be the owner of the index or the table or the database in order to reindex it. When you use reindex, it builds the index contents from scratch, and therefore it has a very similar effect as dropping and recreating an index. However, the way that locks on reads and writes works on them is different. Here are some reindex usage examples. The first example will rebuild the index named MyIndex. The second example will rebuild all the indexes on the table named MyTable. In DB2, the runstats command updates statistics in the system catalog about the characteristics of a table, associated indexes, or statistical views. These characteristics include number of records, number of pages, and average record length. The optimizer uses these statistics to determine access paths to the data. For a table, call the runstats command when the table has had many updates or after the table is reorganized. For tables, this command collects statistics for a table on the database partition from which it is invoked. If the table does not exist on that database partition, the first database partition in the database partition group is selected. For a statistical view, call the runstats command when changes to underlying tables substantially affect the rows that are returned by the view. The view must be previously enabled for use in query optimization by using the alter view statement. For views, this command collects statistics by using data from tables on all participating database partitions. Here are some usage examples. The first example collects statistics on the table only, with distribution statistics on the employee ID and employee name columns. And the second example collects statistics on a set of indexes. In DB2, the reorg table command reorganizes a table by reconstructing the rows to eliminate fragmented data and by compacting information. On a partition table, you can reorganize a single partition. In terms of its scope, the reorg table command affects all database partitions in the database partition group. Here is a simple usage example. This example will reorganize a table to reclaim space by using a temporary table space named mytemp1. In DB2, the reorg index command reorganizes indexes. You can reorganize all indexes that are defined on a table by rebuilding the index data into unfragmented, physically contiguous pages. On a data partition table, you can reorganize a specific non-partitioned index on a partitioned table, or you can reorganize all the partitioned indexes on a specific data partition. If you specify the cleanup option of the index clause, cleanup is performed without rebuilding the indexes. You can clean up a specific index on a table, or you can clean up all of the indexes on the table. In terms of its scope, the reorg index command affects all database partitions in the database partition group. In this video, you learned that optimizing your databases can improve response times and increase overall performance. Relational database management systems provide their own utilities or commands for optimizing databases. In MySQL, you can use the optimize table command. In PostgreSQL, you can use the vacuum and reindex commands. And in DB2, you can use the runstats and reorg commands. Welcome to using indexes. After watching this video, you will be able to explain how indexing improves query performance, create effective indexes, describe the different types of database indexes, create primary keys, create and drop database indexes, and list the considerations for creating indexes. So, what is a database index? Much like the index in a book helps you find information in the book faster, an index for a database makes finding information in the database faster. For example, if you search a book without an index, you must search every page in the book to find information you want. And similarly, if a computer searches a database without an index, it must search the entire database to find the information, which can be very slow, particularly in a very large database. A database index, however, can significantly improve search performance for a database. In a database, the index is essentially an ordered copy of selected columns of table data and is designed to enable efficient searches without having to search every row in a database table every time it is accessed. The columns selected to make an index are typically defined by administrators and can be based on many factors such as frequently searched terms. In this example, we are selecting the customer ID column. Regardless of how they are constructed, the overall goal of an index is to help users find the information they need quickly and easily. So, an index serves as a lookup table with a pointer or link to the original rows in the base table for which the index is created. An index can include one or more columns in the table. However, while indexes can improve database performance, they also require additional storage space and maintenance because they must be continually updated. For any database, you will likely have to experiment with different types of indexes and indexing options. This will help you find an optimal balance of query performance and index maintenance, such as how much disk space and activity are required to keep the index up to date. For example, narrow indexes, or indexes with relatively few columns in the index key, take up less disk space and require less overhead to maintain, whereas wide indexes, while they may cover a greater number of queries, also require more space and maintenance. There are many different types and methods of indexing databases. The main types can generally be described as one of the following. The primary key is a special type of index that is always unique, non-nullable, and there can only be one per table. It is also clustered, meaning that the data is actually stored in the underlying table in the same order as the primary key. Each table can also have any number of additional or secondary indexes other than the primary key. These are non-clustered and can have single or multiple columns. Indexes can be defined as unique or non-unique. Ordering of columns is important because an index will be sorted in the order in which columns are specified when the index is created. Sorting can be ascending, which is the default, or descending, but it will sort by the first column first, then by the next column, and so on. The primary key of a table uniquely identifies each row in a table. While having a primary key is optional in some RDBMSs, it is generally a good practice to create one when creating a table. It may also be possible to add a primary key later by altering the table. The first code block on this screen shows the general syntax for creating a primary key when creating a table. The second code block shows a simple example. This example would create a table called Team with the Team ID column as the primary key. If the primary key consists of multiple columns, you can even specify the primary key constraint after defining all of the columns. You simply add the primary key option, then specify the column names in parentheses. Since primary keys need to have unique values, one way to ensure that is to create automatically generated incrementing values for the primary key columns. In DB2, these are called identity columns, and they can be created by specifying the keywords generated by default as identity after the column definition. And in MySQL, you simply add the auto_increment keyword after the column definition. The basic syntax for creating an index is shown in the first code block. You use the create index statement to define an index, and you use the on statement to specify on which database table to create it. You specify the column names in parentheses, and the order in which you enter them dictates the index's sort order. Here are a couple of examples. The first one creates a unique index named unique num in the project table with a column named projname, meaning that the project table cannot have multiple rows with the same projname value. When the on-table name is specified, the unique option prevents the table from containing two or more rows with the same value of the index key. The second example creates an index named job by DPT in the employee table, and it includes work depth and job columns in that order. This one is not unique, so the table can have multiple rows with the same work depth and job columns, but the benefit of the index is that the query filtering on those fields will be faster than those without an index. To delete an index, you use the drop statement. Dropping an index does not cause any other objects to be dropped, but will cause packages that have a dependency on the dropped index or index specification to be invalidated. This example deletes the index named job by DPT. A primary key or unique key index cannot be explicitly dropped using the drop statement. Deleting the primary index or a unique key index is done through the alter table statement. After the primary key or unique key is deleted using alter table, the index is no longer considered the primary index or unique index, and it can be explicitly dropped using the drop statement. One of the major sources of database application bottlenecks can be poorly designed indexes or a lack of sufficient appropriate indexes. Therefore, designing efficient indexes is vital for optimizing database application performance. When designing an index, you should consider the following core principles. Understand how the database will be used. For example, will it be used for heavy online transaction processing or for the storage and retrieval of large data sets? Understand the most frequently used queries. For example, if you know that a frequently used query joins two or more tables, that may assist you in deciding the most appropriate index type to use. And understand the characteristics of the columns. For example, what kind of data will they contain? Will they contain integer values? Will they be unique? Knowing these characteristics from the outset will help you choose an appropriate index type. You will also need to consider, when creating or maintaining an index, which indexing options will best improve its performance. For example, if you are creating a clustered index on an existing large table, it would be a good idea to use the online index option, as it permits concurrent activity on the underlying data while the index is being built. And where is the best place to store the index? Where you decide to store your indexes can improve query performance by increasing the performance of disk input-output operations. For example, if you store a non-clustered index on a storage group located on a different disk than where the table storage group is located, it can improve performance as both disks could be read simultaneously. In this video, you learned that database indexes can significantly improve search performance for a database. Database indexes can be either primary key indexes or non-primary key indexes, that is, standard indexes. Primary keys can be defined when creating tables. The create index statement is used to define an index on a database table, and the drop statement is used to drop or delete an index. A primary key or unique key index cannot be explicitly dropped using the drop statement. It must be dropped by using the alter table statement first. One of the major sources of database application bottlenecks is poorly designed indexes or a lack of sufficient appropriate indexes. And finally, designing efficient indexes is vital for getting optimal database application performance. Welcome to Troubleshooting Common Issues. After watching this video, you will be able to describe common performance, configuration, and connection issues, describe basic troubleshooting and solutions for common issues, and describe tools used to identify, prevent, and solve common database issues. Troubleshooting is a process of identifying and solving a problem. It begins by answering the following questions. What are the symptoms? Who or what is reporting the problem? Where is the problem happening? Is it specific to a platform, environment, application, or something else? When does the problem happen? Does it happen at a specific time, multiple times, or under specific conditions? Also, under which conditions does the problem happen, and is the problem reproducible? The most common problems encountered with databases are typically caused by one or more of the following. Poor performance. Poor performance can result in slow response to user queries or applications accessing the database. Improper configuration. Improperly configured clients, servers, or databases can cause a wide range of problems, including poor performance, crashes, errors, or even database corruption. Poor connectivity. Poor connectivity can cause poor performance, timeouts, or a variety of errors when interacting with the database. Poor performance is usually caused by high latency for disk reads and writes, slow processing time by the server, or a poor connection between the server and client. Any of these could be rooted in one or more of the following. Inadequate server hardware or configuration. For example, the server could be running out of disk space, memory, or processing power. Increasing these resources on the database server is called vertical scaling. Adding additional database partitions and shards to improve performance is called horizontal scaling. Improper configuration. A poorly configured database may be operational but still unable to meet demand. For example, it may need to allow more connections, or it may need changes to its buffering and indexing settings to keep up with queries and return results quickly. Connectivity. A slow or poor network connection or limited bandwidth between the client and database can cause high latency and processing times. Or queries and application logic. A poorly written database query or improper application logic, such as unnecessary locking of database objects, can also result in performance issues. An improperly or suboptimally configured client, server, or database can cause any number of problems that can manifest in many ways. For example, a user with an incorrectly configured client or incorrect driver may be unable to connect to the database. A poorly or incorrectly configured server can reduce performance, cause timeouts, or any number of possible errors. Or the database may need to be configured to allow more connections or other settings, like caching or indexing, and may need to be adjusted to correct problems or improve overall performance. Common issues with client configuration can be caused by incorrect login credentials, an incorrect hostname or IP address, or even a corrupt or outdated connection driver. To fix these problems, check the client's driver configuration and verify the following. The username and password specified in the connection settings are correct. Be sure to verify that the client is also configured to use the correct type of authentication, such as Windows or SQL authentication, for example. The connection configuration settings, such as IP address, hostname, and server name, are correct. And the driver version for the database application is up to date and correct. Server configuration also significantly impacts performance and operation. Some examples of things you might change or configure to improve performance or correct a problem include add more physical RAM or increase the memory assigned to the server, add more physical disk space or assign additional disk space to the server. Consider upgrading the CPU or assigning more processing power to the server. Consider defragmenting the hard disk. Fragmented data degrades overall performance. Sometimes configuring the storage system appropriately can alleviate performance issues. For example, placing frequently accessed tables on a faster disk. And bugs in operating systems or in RDBMS software can result in errors and server crashes, so ensure you regularly apply software patches and security updates to guard against this. The configuration of the database is something you need to monitor and continually evaluate to ensure it meets demand. Some examples of configuration settings you might need to change or correct are: increase the number of allowed connections to the database to meet increasing demand, change database buffering to improve performance, or change database indexing to improve performance. Poor connectivity between the client and the database server can cause a wide range of problems, including poor performance, error messages, or loss of function. Some of the most common connectivity problems are typically caused by one of the following. The database server cannot be reached or is not running properly. The database instance on the server is not running properly. The client login credentials are incorrect or missing security settings, such as for SSL connections, or the client configuration is incorrect. Here are some common methods to help troubleshoot and solve basic connectivity issues. Verify that the database server is running properly. The exact procedure depends on your configuration and environment. For example, you may need to physically check on an on-premise server, or you may need to verify that a virtual machine in a cloud service is running. Next, verify that the database instance on the server is running. This process varies depending on operating system and database. For example, on a Windows-based system, you could use the Task Manager to verify that the instance is running. Or on a DB2 configuration, you could run db2 cmd.exe and then issue commands in the command line. Verify that the database can be reached from the client. A common method is to use the ping command from the client to communicate with the server's IP address or host name. And finally, verify that the client connection driver is configured correctly. For example, make sure the username and password for the connection are correct, and that the settings like IP address or host name or security and encryption protocols are also correct. Performance monitoring, reports, and server and database logs help identify performance bottlenecks and determine the best way to correct them. Performance monitoring helps identify potential network, server, and database issues before they occur and helps determine where improvements can be made. Dashboards can monitor databases in real time and provide an early warning system for problems before they affect users, in addition to tracking historical performance and other metrics. And server and database logs help identify a problem and when it occurred. In this video, you learned that the most common problems encountered with databases are caused by poor performance, improper configuration, or poor connectivity. Poor performance is typically caused by high latency for disk reads and writes, slow processing time by the server, or a poor connection between the client and server. Server configuration issues, such as inadequate hardware resources or misconfigured settings, can significantly impact performance. Some of the most common connectivity problems are not being able to connect to the database server or instance not running properly, and client login credentials being incorrect. And finally, performance monitoring, reports, and server and database logs can help identify performance bottlenecks and determine the best way to correct them. Welcome to using status variables, error codes, and documentation. After watching this video, you will be able to describe how to obtain server status information, explain how to retrieve error codes and information, and describe how to use RDBMS documentation for troubleshooting. When a database is experiencing a problem, you will first want to check the health and status of the database. All databases have a variety of commands and utilities that allow you to quickly get a snapshot of a database's health and operational status. These utilities are accessed through either typed commands or a graphical interface. For example, from a command line in a Unix environment, you might use the service MySQL status command to view MySQL status. And the output might indicate that the database server status is running or is OK, as shown in this screen image. Available commands and syntax vary with the database you are using, such as DB2, MySQL, or PostgreSQL, and the environment in which you are using the database, such as Unix or Windows. For example, in DB2, you can run the db2pd command to monitor the status of a DB2 instance and run problem diagnostics. For a database using MySQL, you might use the show status command to get server status information. And on a server running PostgreSQL, you might use the pg_isReady command to check the connection status of a PostgreSQL database server. Databases use many status variables to provide information about their operation, and status variables can be either global or session-based. A global status variable may represent status for some aspect of the server itself, for example, aborted_connects, or the aggregated status over all connections to MySQL, for example, bytes_received and bytes_sent. If a variable has no global value, the session value is displayed. A session status variable, sometimes called a local status variable, represents values for the current connection. You can also use a like clause and pattern with a show session statement to show status variable information that matches a specific pattern. For example, if you used the statement show status like key%, you would only see the status for variables with key in the name. In addition to commands, you may also have a graphical interface with dashboards and reports for monitoring database status and information in real time. For example, on a Microsoft SQL server running on Windows Server, you could use Activity Monitor to get information about SQL Server processes and how the processes affect the current instance of SQL Server, and use System Monitor to verify status and monitor SQL Server performance. There are many possible log files you can use to help identify when and where an error occurred. The most used ones are server and operating system logs, which log general server activity, connectivity, and other aspects of the server or servers running the database, and database error logs, which log information and errors specific to the database being operated, such as MySQL or PostgreSQL system. Log files are important tools for discovering when an error occurred and the description of the error. For example, in a typical SQL server, some of the most accessed logs are the error log file, which is created every time SQL Server is started, the event log file, which shows informational and error events, and the default trace log, which is an optional log file that tracks all database configuration changes. Whether you use log files or receive an error message, you will most likely need to interpret specific error messages and error codes. For example, error messages or logged errors may contain a message and ID number that can be used to troubleshoot the problem. They may also contain other information, such as the name of the procedure that caused the problem, the state of the database when the error occurred, and additional descriptive information, the severity of the problem, or both. You might also see a line number referenced if the problem occurred in a script or batch file. After checking database status and compiling information, your next step is to learn more about the error you are experiencing. There are many documentation and help sites available on the internet with error code tables that can help you decode and correct errors. Popular resources include, for IBM DB2, information can be found at ibm.com/docs/db2. For PostgreSQL, information can be found at postgresql.org/docs. For Microsoft SQL, information can be found at docs.microsoft.com/sql. And for MySQL, information can be found at dev.mysql.com/doc/. In this video, you learned that databases have utilities to check health and operational status. The available commands and their syntax vary with the flavor of the database you are using. Databases use many status variables to provide information about their operation, and status variables can be either global or session-based. Databases may also have a graphical user interface with dashboards and reports for monitoring database status and information in real time. There are several log files you can use to help identify when and where an error occurred, and there are many documentation and help sites available on the internet with error code tables that can help you decode and correct errors. Welcome to Using Logs for Troubleshooting. After watching this video, you will be able to describe diagnostic logs and their purpose, list various types of diagnostic logs, identify types of information included in database diagnostic logs, and explain where diagnostic logs are stored and how to access them. Troubleshooting is a systematic process used to locate the cause of a fault in a computer system to provide details on correcting the relevant hardware and software issues. Approaching troubleshooting using a logical and systematic approach is essential to a successful resolution. Troubleshooting is one of the main reasons people create logs. When a problem occurs, you'll want to diagnose it to understand why it happened and what the cause was. A diagnostic log tracks what is happening in a system component or an application, such as a web server or a database. It contains information about an event or a problem encountered when processing requests. The diagnostic log is a record of significant events and errors in chronological order, and is very useful for diagnosing and troubleshooting problems. For example, if a web server receives a request to load a file that is missing, this error and its details can be logged to the web server log. The diagnostic logs are also sometimes referred to as troubleshooting logs, error logs, or event logs. It is essential to recognize that they may contain events, informational messages, warnings, or errors and their details. An event might be when a user connects to the database. or an informational message that includes information on a particular subsystem status. Additional events may be a warning message that might indicate that disk space for the database volume is running low, or an error message that contains details about a failed database backup operation. Some logs may have fewer or more categories of diagnostic messages, such as fatal and panic as additional classes of errors, or may label them differently, for example, note or notice instead of information. A database administrator needs to be familiar with various types of diagnostic logs in the system. These include logs for server components, storage and other hardware devices, network, operating system, applications, and databases. While the systems administrator may monitor the other logs, the DBA needs to be intimately familiar with the database diagnostic logs and review them frequently. These database diagnostic logs are generally separate from the database transaction logs or query logs. In most cases, you can configure the location of the log files. However, certain logs, such as system log files, may have a fixed location. Many log files are recorded in plain text, and any text editor will do just fine to open them. For example, on a machine with a Windows operating system, double-clicking on the log file will open Notepad by default. However, some log files are machine-readable and may require particular viewers to view their contents. Diagnostic logs can contain a variety of information. Some typical components of messages in a diagnostic log include the type and severity of issue, whether it is an event, informational, warning, or an error, the corresponding error code and message, the location, URL, or subsystem where the error occurred, a timestamp, the user's IP and user agent, and finally, any additional information depending on the event or error. Here is an example of a message in the db2 diagnostic log file called db2diag.log, which is in ASCII or plain text format, and which you can view using a text editor. It includes a timestamp of when the message was logged, the type of message. In this case, it is an event related to starting the database manager initiated by running the db2 start.exe. It also includes additional details such as the db2 software, fixpack, and operating system levels, and information about system resources, CPUs, and memory. Using the db2 Database Manager configuration, you can configure the location of the db2 diagnostic log and the severity or diagnostic level of messages to log. Similarly, the PostgreSQL database typically logs all events like startup and shutdown, errors, connection issues, and so on. You can configure the location where the log entries are stored using the log destination parameter in the postgresql.conf, the syslog in case of Linux and Unix systems, the event log in case of Windows systems, to a CSV log file that you can easily import into a table and query the log entries using standard SQL statements, or to stderr, short for standard error, which is the default and typically outputs to the console, but can be configured using log directory parameter to specify a particular location, the default being pglog. You can also select the format of the log file name that names the log files based on a specific string pattern that can include a timestamp. In MySQL, distinct from the binary or the transaction logs that are used for recoverability, you can use other server logs for troubleshooting problems. These include the general query log, which logs connections and queries received from clients, the slow query log, which, as the name implies, logs queries that take longer than a specified time to execute, and, most importantly, the error log file that contains diagnostic and error messages from MySQLd, the MySQL daemon or server process. In addition to the error messages, the MySQL error log also includes warnings and notes during database server operation, startup, and shutdown. You can configure MySQL to write messages to the Windows event log, which is the default setting, the syslog or system log on Linux and Unix-like systems, the stderr or standard error, which is the default on Linux and Unix, or to a specified file. You specify the file name for logging messages using the log error option in MySQLD or the MySQL configuration file. DBAs can configure how much information is stored in the error log, choosing between Level 1, Errors Only, Level 2, Errors and Warnings, and Level 3, Errors, Warnings, and Notes. Level 3 is the default. The verbosity of messages is specified using the log error verbosity option. In this example, the log error verbosity setting is 2 errors and warnings only. In this video, you learned that a database administrator needs to be familiar with many types of logs, especially the database diagnostic logs. A database diagnostic log file, also known as an error log or troubleshooting log, contains time-stamped messages for various types of informational, events, warnings, and error details. Most diagnostic logs are text-based and can be viewed on the console or in a text editor, but some may require special tools or viewers to view and filter their contents. Most databases provide settings for enabling and configuring diagnostic and error logging, such as setting log file names and locations and verbosity of messages. And some databases, like MySQL, offer more than one diagnostic log, for example, the error log and slow query log. Welcome to Overview of Automating Database Tasks. After watching this video, you will be able to identify what database automated tasks are, explain the benefits of scripting to automate tasks, list some of the database automation tasks, describe the benefits of automating tasks, and recognize the vital role automation plays in database testing. Database automation uses unattended processes and self-updating procedures for administrative tasks, leveraging existing processes and tools to make administration tasks simpler and quicker. Results in fewer deployment errors and higher reliability and speed on change implementations. Frees up staff otherwise occupied updating code and performing other work. And works best with tasks that are time-consuming yet repetitive, such as database health check, alerts, and server or database maintenance. Script automation is the process of using software to leverage and reuse existing scripts to deliver automation in a managed framework without requiring custom scripts to be developed and maintained each time. Scripts are written to carry out routine yet important jobs, which include backing up and clearing event logs, automating networking tasks, monitoring system performance, reading and writing to the registry, managing various user accounts, computer accounts, printers, and applications and services. There are several methods and tools for automating most database administration tasks. Some of these come built into a database, and others are performed by DBAs and developers either via scripts or database code. Common scripts that DBAs can write include processes to backup, truncate, load, and restore databases. When writing, updating, and maintaining scripts, it is important to have a version control system that keeps track of and retains an incremental history of code and database changes. If necessary, the DBA can restore the database to a previous version if an error or other issue occurs. Database scripts work best when developing within a version control environment. The primary goal is to keep the code in sync with the database. You can also write scripts to perform certain database administrator or DBA tasks, such as sending error notifications, moving archive logs from one storage to another storage container, scheduling reports, and so on. DBAs can also create scripts that are useful for deployment of code changes from database to database. There are several ways for automating most database administration tasks, and these include tools or schedulers, such as cron jobs, and scripts using Shell, Python, or other scripting languages. There are many good reasons why you would want to automate database tasks that include to increase throughput or productivity, to improve quality or increase the predictability of quality, to improve the robustness or consistency of processes or product, to increase the consistency of output or results, to free up workforce to take on other roles, and to provide higher-level jobs in the development, deployment, maintenance, and running of the automated processes. You can automate tasks such as database health check, the process of inspecting a database to see how healthy and efficient the system is; alert log file cleanup, the process of deleting the chronological log of messages and errors written out by the database. Typical messages found in this file include database startup, shutdown, log switches, space errors, and so on. Trace file cleanup, the process that deletes the trace file or backup file, which is a snapshot that shows the process that was executing and modules that were loaded for an app at a point in time. And data dictionary statistics, the process where the system gathers a collection of names, definitions, and attributes about data elements that are being used or captured in a database, information system, or part of a research project. A data dictionary provides metadata about data elements. You could also automate database configuration check, the process to check to see whether your database configuration still complies with the current recommendations for your system. Schema object check, the process of monitoring your database changes to quickly identify the weak links and problematic queries. And routine daily tasks using GUI tools, the process of performing everyday functions in the database with a GUI, for example, running reports and backing up files. Database testing involves checking the database to ensure that everything is correct and running properly using a controlled testing environment. Database testing involves checking the schema, tables, triggers, and so on. Database testing is important in software testing because it ensures data values and information received and stored into the database are valid. Database testing helps to prevent data loss, saves aborted transaction data, prohibits unauthorized access to the information, and checks the integrity and consistency of data. Automated software testing can look inside an application and see memory contents, data tables, file contents, and internal program states to determine if the product is behaving as expected. Once created, automated tests can be run repeatedly at no additional cost and are much faster and more secure than manual tests. Automated tests can increase the depth and scope of tests to help improve quality and security of automation database testing. In this video, you learned that database automation is the use of unattended processes and self-updating procedures for administrative tasks in a database. Scripting languages easily automate processes at the application level. Some automation processes include backing up, truncating, and restoring databases. Some of the advantages of automating database tasks include increased throughput or productivity, improved quality or increased predictability of quality, and better consistency of processes or product. And finally, automated database testing has many benefits, including being more secure, cheaper, and faster. Welcome to Automating Reports, Notifications, and Alerts. After watching this video, you will be able to distinguish between reports, notifications, and alerts, describe how DBAs use reports, notifications, and alerts, identify some common alerts based on best practices, and explain some ways of automating reports, notifications, and alerts. Imagine you're a DBA working for a small company, and each week you need to give your bosses the status of the databases for which you are responsible. How will you get that information, and what should you include? Our DBMSs include reporting functionality that gives you insights into the health of your databases, like the number of users connecting successfully or failing to connect, the amount of space used and the rate of increase, and the number of queries executed against the database. You can create and configure reports with specific metrics to give you the information you need. Running reports on database health allows you to address issues before they become serious problems, while allowing you to keep track of trends over time and help you to predict future needs and prepare for them. You can automate reports to run daily, weekly, or monthly, depending on your needs. In larger companies, an entire department may manage automated reports, while in smaller companies, a few DBAs, or in some cases, only one DBA, might perform that task. Some companies use third-party reporting tools that provide extra options and features. Whereas reports give a regular overview of database health, notifications are used when an issue should be tracked, but doesn't require your immediate attention. Notifications give you, the DBA, an opportunity to track specific database events. You might choose to be notified when a user attempts to log in but fails. A few events like this are part of daily life, as users forget or mistype their passwords. But a cluster of login failure notifications may indicate a malicious attempt to gain access to data. You can receive automated notifications through SMS messages, email, or via a dashboard. You need to configure your preferred option. Alerts quickly make you aware of issues that require your urgent attention. They are triggered by events like catastrophically low drive space or memory, scheduled jobs that have failed to complete, or error level events in the error log. You need to determine which alerts are appropriate for your environment and configure them to immediately reach the DBA on duty. When configuring alerts and notifications, be careful not to set so many that you cannot respond to them all. You should evaluate which ones are vital and configure them accordingly. Alerts use 2 or more thresholds to help communicate the severity of an event. A warning threshold when the system sends a warning message, and a critical threshold when the system sends a critical alert message. A best practice is to send out warning alerts when the threshold for the specified event reaches 85%, and a critical alert when the threshold reaches 95%. You can customize these values to suit your environment. Now that you know a little about reports, notifications, and alerts, let's see how to automate these features. Most RDBMSs enable you to configure the content and frequency of reporting through a graphical interface. Many provide sample reports and enable you to configure your own if necessary. Notifications and alerts function similarly, and you can configure them through a graphical interface, a command line tool, or a script. The process of automating reports, notifications, and alerts varies depending on which RDBMS you are using. In this video, you learned that reports give a regular overview of database health. Notifications give a forewarning of a situation that could become troublesome if not addressed. Alerts bring awareness to an issue that needs immediate attention. And DBAs automate reports, notifications, and alerts to suit the needs of their environment.